Thank you for coming today. It's the first talk, so yeah, I know you're all here. But it may be a bit too low level for some of you, maybe not. Do we have any cryptographers on? Jesus. Okay. I get it just one, so yeah. You know, the crypto stuff, the blockchain is very trendy now. It can be very rich. It is basically a new gold. There are a lot of it, like Litecoin, Bitcoin, Ripple. You don't really know what to use, what to buy, and that will be basically crypto for beginners. Okay? Oh! That's the funny part. We got the emergency alert that the crypto stands for cryptography, not for cryptocurrency. That is the common confusion these days. My name is Marcin Krzyzanowski. You can find me on Twitter. My handle is my last name. I have a blog. I blog about Swift mostly. I have a GitHub account where I do some open source. I will just outline two projects. One is CryptoSwift that this talk is based on, and the other one is Objective PGP, that is implementation of OpenPGP for iOS. I work at PSPDFKit. PSPDFKit is a company that delivered the best PDF framework for iOS, Android, and web. So you can buy it if you need. This talk is based on the CryptoSwift project. This is the project I work on for about 4 years now. I implemented crypto primitives in Swift. Crypto primitives are the most basic structures in cryptography. You build protocols based on that. Okay, let's start. Yeah, I will use some of the issues that were reported to the project to show you the real uses or questions that I got, and they are most common in the issues tab. There are, you can see, almost 500 issues. I already closed like half of it, about 50% is about CocoaPods, Carthage, and Swift versioning. The rest is about how to use the crypto, what I'm doing, that kind of stuff, and the remaining about 10% is actually the bug reports and the feature requests. So that's fun. Let's start with this one. It was reported not that many years ago, days ago, and is the most common one. The problem is string cannot be reproduced from the encrypted uint8 array. And the expected behavior is wrong, but it crashes. Like, this is the report I got. What do we have here? Assign int8 is a byte, which is 8 bits, right? Do we agree on that? Are we? Okay. It was true, always true in the history of the computers. Well, it wasn't. Like PDP-10 uses 7 bits per byte, and actually for different languages there's like a constant. Even for C language there's a constant then where you can specify how big is the byte. But we will assume for the rest of the talk that 8 bits it's 1 byte. That will be easier. And what is going on here, I'm looking here, but I should be looking here. He's doing the encryption, doesn't matter. He's doing the encryption, and this line here says print string from the cipher. Cipher is the ciphertext using the encoding UDF-8. Do you know Swift? It's not that obvious. Okay, if you know Swift, this is the exclamation sign, so that means enforced unwrapped. And it crashed. It crashed because this this method returns nil, right? And it's kind of unexpected here. So I draw the diagram to show you what is going on here. So we have a string, it's lorem ipsum here, that can be represented as an array of bytes. Is a hexadecimal here. Each byte is a series of bits that then go to the magic machine of encryption. It do its job and output with bits that can be represented as byte. And eventually we want it have it as a string, right? This is where the things go south. To understand why it is a problem, we have to know what is a string, right? In the history of computers. So in C, a string is a series of bytes, and the last byte is 0, right? That's the C string type of notation. In Swift, that will be a struct with the array of characters and a property that says how long is the string, right? So let's assume we're in a C world, and during the encryption we got the 0 at start, right? If we treat the ciphertext as a string, that will the result would be just an empty string, but that's just the language nature. In Swift, well, internal representation of a string in Swift is UTF-16, so it used probably 2 bytes, or not necessarily, but about 2 bytes per character. But here we use UTF-8, right? So what we are trying to do, he tries to do to represent arbitrary bytes as a string, and it's basically a wrong assumption. It won't work always, because the result of encryption is almost random. It's not random. It should look like random. So we don't really know what we get on the output, right? That's just not string. We can do that string, but yeah, to have it to represent it as a string, we have to use encoding. And this is the confusion, encryption and encoding. I don't know, it sounds kind of similar, so maybe that's the reason. But the encryption works on, actually it works on bits, but let's say bytes. So it encrypts byte to byte. And encoding is a different representation. And if we want to represent the array of bytes as a string, we can use base 64, right? The base 64. You're familiar with base 64? Yeah, it's the most common encoding. Use just 64 characters to represent 255 values. Or the hex string representation is just hex values byte by byte that can be written as a string. Right. What is the encryption? Yeah. So in encryption, in cryptography, there is one gold standard. It's called one-time pad. It's known since 19th century, I believe, right? I'm looking at you now. So if you either say, yeah. It's called one-time pad. It's a encryption technique, but it's like a cipher that cannot be cracked. The thing is, it's very hard to use. How it works? It's basically for your plain text message, you have to have random key. For each position, there's a mapping. Like there's a mapping. It's not that A is L, because here L may be something different. You know, it's random series. You do some operation for between key and plain text and get a ciphertext. Like today we would use the XOR operation. In that days there was some addition operation. Now, the problem with that is we have to have as long key as the message is. So you can imagine if you want to encrypt PDF, you need another file length of the PDF just for the key, and then you have to share that key. Well, it's very problematic. We don't use that in practice. We use short keys that are expanded to everything else. And there are two types of encryption. I will talk about mostly about symmetric, but I will mention both. The symmetric key encryption. The symmetric key means for the decryption and encryption, you basically share the key that you have to use, and you put to the magic box. How it works? Well, today it works XORing, by XORing. Are you familiar with the XOR operation? Okay, there are many of you who are familiar, but some of you are maybe not. So I have this diagram. XOR operation it's exclusive OR, and why it is in use? Because there are 50 chances that for given input, for the pair of the values, you will get either 0 or 1, right? So it's equal. You don't know. It is like here. Like here, if you use AND, well, you will get most likely 0. If you are OR, most likely 1. But with XOR, you don't know, so there's no advantage. The another type of encryption is asymmetric key encryption, and this is the RSA, public-private key, you may know, and it's based on that. The math is hard, especially for the computers, but for people as well. So as long as a few years still to the post-quantum computing, we can still use the current algorithms, but there work there are people who design the ciphers for the post-quantum computing. It's based on the math that it's hard to find two numbers, right? We are the iOS programmers, probably. And if you, let's say you have a task to encrypt data, you Google and you go to Stack Overflow, and most likely you will find this snippet. This is a common crypto. Common crypto is a system library that is part of the iOS and macOS systems. And function cccrypt is the most general function you can find there. It has 12 parameters, and you have to choose wisely how to fill it with data. Actually, it doesn't look good here. This is the another version of CC crypto. But there are 5 parameters you have to choose. You have to know the values. The first one is block mode. What the hell is block mode, right? Then algorithm, you can be familiar. Yes, probably, because that was in a snippet. Then there's a padding. Okay, just choose whatever there is. IV, please. What is IV? Who knows what is IV? Okay, the 3 people. And the key, right? So you will put the password here probably, because why not? And the other one, you don't just even care. There are zeros. Yeah, so we only care about these 5, and I will go through these 5 values, so you get some information how to choose that, how to use that. And just for the record, this is how it looks in the CryptoSwift. The same. Either it may look a bit nicer. You still need to choose those 5 parameters. This magic box that do the encryption is a cipher. It's an algorithm that is designed. You do not come up with your own. You just use the ones that are, widely proven to be secure. The most popular and at least mathematically proven is the advanced encryption standard. Yeah, it's a standard. It's a good cipher. It's a fast cipher. The part of this cipher calculations are parts of our processors. It started with Intel, but it's also part of the REM. So this is fast, right? And everyone used that, you know. We have two kinds of ciphers. There are stream ciphers and block ciphers. Stream ciphers are designed to work with the stream of data. You know, stream of data is just arbitrary number of bytes that get encrypted, and you get the output right away, just encrypted output. And there are block ciphers that work on a block of data. That means it can only encrypt a block of data, not just 1 byte, but just a block by block. Oh yeah, block by block. IS is the block cipher. It uses 60 bytes per block. So the minimum, the shortest message you can send to IS cipher is basically 16 bytes. To make things a bit harder, these block ciphers have operation modes. It's called cipher block mode, and there are more. I just saw here 3, and we'll discuss 2 of them. First is a CTR, that is counter block mode, and it does some magic because it makes a stream. It allows you to use block cipher as a stream cipher. So if you need to encrypt a network, you should take a look at the CTR block mode. I will just skip ECB because you shouldn't use that, like never. And CBC is a block mode. It doesn't make sense. It should be cipher blockchain or something like this. Yeah, cipher blockchain. I showed that one because it's most likely the default one for the library you will work with. Okay, let's go through how it works. Counter mode. It gets some counter here, and nonce, doesn't matter. It gets some counter, do the encryption, apply key, XORing, output with ciphertext. Next, the counter is 1, the counter is 2. Do the same. What's important here? It's independent, right? Each block can be encrypted independent. That means it can be parallelized. You can encrypt with this mode. You can somehow use, just chunks of your message and encrypt that independently, so it may be faster. And the CBC, for change, is different. It gets some initialization vector, apply key to encryption, return with ciphertext that is used here in the next block, the same here. So the output is used as the input for the next block. So it can be only encrypted linearly. Yeah, that's one of the property. And the IV, the initialization vector used here, what is it? You can find a name nonce, which means arbitrary number that can be used just once. IV is the only value that puts some randomness to the encryption. Otherwise, it's not random. IV should be unique. It depends on the cipher and on the block mode, but For CBC, it should be unique, should be used just once for the message, and you should regenerate the new one for the next message, right? It's not something that you just you have it in a const, property and reuse it. You just have it new, and it's public property. Usually, let's say this is the message. Usually, the initialization vector is at the beginning, so you need it to decrypt, and the ciphertext goes after that. But I don't know why it's moved. What's going on in Common Crypto if you use a CBC mode that is default for this function? And you figure out that you can actually pass nil here in the IV value. Well, it will be fine. There's no even warning. It will use IV of all zeros. And I just said that you should never reuse the IV with the same message. So yeah, it's basically misuse of the CBC and IES mode, and it's part of the Common Crypto. It's worth to know that the bug is reported, but Apple doesn't seem to care. Okay, let's move to the next one. Next one. The question here is, I'm using an Arabic number and it crashes. So yeah, I tried to reproduce. I was unable, and at the end, there are a few parameters. He said, okay, I'm using CBC, and I'm using no padding. This is the I think it's the last property. No padding. What does it mean, no padding? You know the padding word, right? It's something like to align to something. In cryptography, well, we have three kinds of padding that you can use with your cipher. One is PKCS5, the other one PKCS7, zero padding and no padding at all. That will be the PKCS5/7 is the most popular. What does it mean? You remember, this is the block cipher, so you have to send 16 bytes. But if you have just 4 of them, what do you do? Well, there have to be something, right? Because you cannot just send 4 bytes. So the idea behind the PKCS5 is, okay, for the remaining bytes, just put the value of the missing bytes. Like here, we're missing 12 bytes, just put 12. And when it's decrypted, the decryptor just check the last byte, say, okay, it's 12, okay, I just discard the 12, and I know the clear text is text. It's similar with the zero padding. The idea is to put the zeros there, but unless your protocol doesn't specify that you should zero padding, don't use that. Because what happens if my plain text is actual 0, last value 0? Well, it will be discarded, right? Because the idea is to discard all the zeros from the end. So you may lose some data. And no padding is just no padding. No padding you can use for the stream ciphers, basically, where you can actually send the arbitrary length of bytes and get the result right away. There is a padding oracle attack that is quite interesting, and I will show you how it works. It's just based on the information about the padding for the cipher, for the ciphertext. It's there are some pre-assumptions to have this to perform that padding, but yeah, it's quite interesting. The name Poodle attack. The Poodle attack you will find with the SSL version 3 and TLS up to 1.2. The TLS 1.2 is the currently most used version, but we are transitioned to 1.3, where the Poodle attack is no longer possible. So yes, just to know that what I show you is possible to do on the internet, right? Everywhere. There are some mitigation though, so it's not that easy. But yeah, we should really quickly upgrade our TLS, our SSL stack on servers and on browsers. Browsers are already there. Okay. I will go through this quickly. One of the property of this is the attack against the AES CBC block mode. One of the property of the CBC is that if I change 1 byte in a ciphertext, it will propagate to change 1 byte in the following block, right? So what I'm doing here, I'm modifying the previous ciphertext. So I intercepted at least two blocks of the message. But it's ciphertext, so yeah, it's public. I can do that. And this is the only knowledge I have. Right? This is the operation that will be done, let's say, on a server with decryption. And this is something, yeah, I will use to hack the system. What I'm doing, I'm modifying this previous ciphertext block to something, doesn't matter. For each change, I send these two ciphertext to the server, let's say, and ask if the decryption succeed or failed. Like here, it succeed. I changed that, it succeed. Third, it failed. What does it say to me? It basically says to me that the padding of the last block is 6. Because it was fine here, not fine here, right? So I know this is a 6 value, and what I'm interested in are basically those 2 bytes to decrypt. So yeah, this is 6, but how would it be if I change that to 7 and just move it a bit further? Yes, I modified the ciphertext to match the value. Doesn't matter, it was 9E, now it's 9F, it's 7. I go here, and I'm attacking this byte. I start with 1. Does it, well, and I get an error, because, well, it doesn't match. So I'm trying all the values here. 0, 1, 2, 3, until I get the success. And the magic is happening because I get a success at some point. If I get a success, I know this equation is true. So I'm doing it just looks like that, but it's not complicated math. I calculate that value out of these two, right? And the result is 47. What I just did, I just guess the plaintext value I guess the plaintext value without knowing the key. All I knew was there is a padding, right? So it's quite strong attack, and you can decrypt like that the whole message. So you really just need 2 factors. First, the message has a user padding. And you can ask as many times as you want the padding oracle or the server, and it will always respond to you, basically. If there will be like a throttling, or just you can ask just 3 times, yeah, we will take more time. But otherwise, yeah. On the mother computer, if that will be local, that will be a few seconds to get the message decrypted, and no key involved. Yeah. Okay, there was that. Next is compatibility. Normally, you know, the crypto algorithms are really well defined. They are standards. So the basics should be compatible between the implementations. The problem is when some inexplicit information is added or used during the encryption, like here. There was a question between, somebody asked, I'm using PHP and it's not compatible with the CryptoSwift. And I start digging and find that he uses actual some framework that instead of return just a plain text, it returns JSON. It's some JSON with the IV and the MAC value, and it's base 64 encoded. Just, it's a different format, right? So you have to know what's going on there to compare with another library. And the same with the OpenSSL. Let's say you have a code, even in when you use OpenSSL as a library, and you try to compare that with the command line. Well, the command line will be different, because from the API you will get just a raw ciphertext, but from the command line you will get the message formatted with something like this. Let's say for this command, when the salt is used and some password, there's like IV, then is string salted __ 8 random bytes and the ciphertext. So you somehow have to know that what you really want to compare is just this value, right? It's not obvious to know. So that kind of checks are not always correct. Here is a Crypto.js. Crypto.js is a library. I don't know how it's popular today, but it was quite popular some time ago in the JavaScript world. What does it do? I think I have, somebody said, I encrypted with the CryptoSwift, I cannot decrypt with the Crypto.js. And I had to take a look in the Crypto.js sources to figure out what's going on. And what's going on here is that when you feed the Crypto.js with the password, it apply that kind of function, IVP bytes to key to the password, produce a key. That key then is used to encrypt data, and then you get a ciphertext. How the hell do you know that this kind of function is used by the JavaScript library, right? There's no way. And especially that this function comes from the OpenSSL, but it's deprecated in OpenSSL. So back then, it was probably added to compatibility with OpenSSL. But today, OpenSSL would rather not use that function, would use PBKeyDF2 function, which is key derivation function to produce key from password, because password is not a key. You shouldn't really use a password as a key. The password is just a password. It can be a cat name or something. But the key is pseudo-random value that is more secure to use by the cryptographic algorithm than arbitrary text. So there we have a key derivation function. It works easy. You get the password on input, do some magic, and this magic is algorithm of the function. There are few at least, and you get a key out the output. So you always should do that change, right? Okay, so at this point we know what the IES work, how it works. It was block cipher. What the key is not a password basically. Block mode, that there is CBC that need unique initialization vector, and that you should use a padding for that kind of cipher. And there's something more. It's called MAC. Do you know what a MAC is? Okay. MAC is message authentication code. You know what the hash is, right? Yeah. So you can think about hash, but it has a different properties. A bit of different. It's just a value that you compute over the data. It's also known as a tag. It gives you the integrity, information about integrity of data you calculate that over. And it uses a key as one of the inputs. So for hash, there's no key, but for MAC, there is a key, maybe key that you use for the ciphertext as well. Let's assume this is a message you're sending. There's IV you put on the front, there's a ciphertext, and then you calculate over that, you calculate tag, and you put it at the end. So when you decrypt, you check the tag, you get this value, calculate on your side, and you know if the message was modified during the transport or not, right? So there is integrity. Yeah, that's how it should be used. So the MAC is calculated over everything. I'm sorry that Rob Napier is not here, because he will be later. But Rob Napier has this library, REncryptor, which is very good, and you should use it. And it has an issue at version 1, where he calculated the MAC just over the ciphertext. So there was IV, ciphertext tag, but the tag was calculated just over the ciphertext. What does it mean? That means you can modify the IV that will change the ciphertext that can match a different tag. It's a kind of it's probably chosen ciphertext attack. It doesn't work always, but that means you can modify the message and will still match the tag or not. It's fixed though. It's a very good library, REncryptor. You should use that. That kind of issue was also a part of the iOS 9.2 that was fixed in iOS 9.3. Well, they just didn't use, they didn't calculate the MAC over the value, and it was possible to. That's not me. That's not me. Okay. It was possible to decrypt the iMessage on a device. They fixed that with the patch on version 9.3. And the last thing is key exchange. So this is the it should be asymmetric cryptography. Diffie-Hellman, you know that? Yeah, RSA that we all know. Public key, private key cryptography. Public key is used to encrypt data, and private key is used to decrypt by the receiver. Diffie-Hellman, they published the paper, but you know NSA says that they know that math 10 years before, but there's no proof. So they just say that. It is used to exchange keys because asymmetric cipher is slow, at least slower than the symmetric like AES cipher. So the best use would be use that encryption just to exchange the symmetric keys, and this is how it works in BASIC on the SSL level. So yeah, you generate a session key on one side. It's just a random value. Encrypt with the public key, send it, the receiver decrypt the session key, and you have a AES encryption established. And then you just use the one-time key on the over the AES encryption that is fast. That's how it basically works. Let's summarize. Cipher can be block or stream. Block always of the block length. Stream, Yeah, I didn't give you the name of the stream ciphers. The name will be Cha-Cha or Salsa. Very catchy names, but it works. The Cha-Cha is actually quite popular. Cipher operation modes, the most common is CBC. So this is how the blocks are connected. IV nonce should be random and used just once for the message. Password is not a key. You use the derive function to get a key from password. Padding can be dangerous, as I presented with the attack, but we should use the padding. Yeah, padding is required, but can be dangerous. I don't know what ways. And authenticate, always authenticate. Authenticate the message with the MAC to integrity, to check the integrity, because really the cipher, how it's called, something like change cipher attacks. It's very common. If you can't change ciphertext, you can change the plain text. So yeah, with the tag, you can check that it wasn't changed during the transmission. And use RSA to exchange IS keys. That will be all. Thank you very much.
Вопросы у кого есть? Вот в конце зала.
Hi, thank you for your talk. Am I right that MAC, message authentication code, is just a checksum of message, or it has any other capabilities? Thank you.
Yeah, it's a check, but it also uses a key, so it's not just the hash code, right? For the hash, you just calculate a hash and that's all. The MAC, for the MAC, you put the key as well, some key, so it gives you authentication capability. And there are two things with that. You can think that it's kind of like a sign, signature, right? And yeah, you can think about like that. Although it, I don't know if I need that. Although it uses the shared key. That means if you share the key, you share key at least with one person. You don't really know who signed that. This is why the public-private key is more not secure, the better solution, because the key is always assigned to one person, so you know who signed that. Here, whoever know the key, the shared key, can sign that data. And yes, this isn't just a number that is calculated over the data, but one of the input is the additional key. Yeah.
Hello. So I wanted to ask about the padding. So when you have, for example, some large text, do you have the padding only at the end? Because so only, for example, at the last block. Yes?
Yes, yes. The padding goes at the last block. Yeah.
And so the previous blocks, they have no padding.
Because you have to send a full blocks previously.
Yeah. So and then. So the next question is about the puddle attack. So because you don't have the text, the encrypted text in the first place, you only have the cipher. So can you tell me, even if you know padding, that helps you only with this last block, or maybe I didn't understood?
Yeah. So you intercept the message, a message basically. And you know what was the end of the message. And based on that, you get the last block and the previous block. So yeah, like in network communication, if server send a post, let's say post message, right, to HTTP, this is not too long message, and you can intercept all of it, being either man in the middle of just or some injected code in JavaScript on the page, right? Yeah, and you probably figure out when it ends, and based on that, yeah.
Okay.
Yeah, it's based on the last block, then you go backward.
Okay.
Больше нет вопросов? So now you can choose the question you like most. And the person
Can I
gets
just
it.
do? Jesus, can we just do a lottery? Something I don't really want to be in that position. The first one was about. I like the first one about Max. Sorry, I know you're very. Yeah.
Ну все, давайте поблагодарим.
Thank you very much.